Okay. So today we're lucky to have Trevor Campbell, who's visiting us from up north, just a 3-hour train ride away, at UBC. He is an associate professor, in the Department of Statistics there. So he received his PhD from uh, Lids at MIT and then spent a bit of time doing a postdoc there at, again, CSAIL and IBSS. Postdoc advisor was Tamara Broderick. PhD advisor was Jonathan Howe, who I just learned about today. I was not aware of him. He has an interesting background where a lot of his kind of PhD time was spent in the engineering world. So you'll see in his talk some of his background really shine through, which I think is what makes Trevor particularly interesting. He's done a lot of interesting work. His research focuses on automated, scalable Bayesian inference algorithms, variational methods, Bayesian nonparametrics, and Bayesian theory. He's received the Blackwell Rosenbluth Award from ISBA and the PIMS UBC Mathematical Science Early Career Award from the PIMS Institute, and the Open Educational Resources Excellence and Impact Award from UBC for his textbook, which he's authored, and it's called A First Introduction, Data Science, A First Introduction. On a personal note, well, it's the first time I'm meeting Trevor, but I've interacted with him through his material. He has a lot of interesting open source material. One of them that I use regularly in my class is a nice lecture on how to give good presentations. So I've benefited personally from it, and I also talk about it with people in my classes. So I would definitely look at it if you haven't. And so please welcome Trevor.
Awesome. Thank you. All right. So thank you for the very kind introduction. And for the invitation to come and speak at the department. I'm excited to meet a lot of you today. Yeah, so this talk is about computational methods in Bayesian statistics, generally speaking. The thing that kind of compels me, I think, the most about the Bayesian methodology is that it sells itself, or at least in theory, it is ideally a black box, right? It's a black box method. You can spend all of your creative and intelligent effort digging into model design and making a plausible model for your data and injecting all of your expert knowledge into the problem of creating a good prior. And once you've done that, the rest of it is just hands off, right? In theory, you get the posterior and life is good. You can answer whatever inferential questions of interest that you want. In practice, I think many of us would very quickly admit that it is not at all that automated, right? Typically in practice, what happens is you need someone with a PhD in computational statistics to sit down and probably write a bespoke sampling algorithm for whatever model you've come up with. And at the very least, you need someone with expertise to babysit the algorithm, tune it, look at diagnostics, check sort of nuanced failure cases, right? It's a very sort of broad procedure. So the goal of this collection of work that I'm talking about today is to bring Bayes just a little bit closer to where we would actually like it to be, which is put all your effort into creative model design and prior design, and then the computational side of things is kind of hands-off. All right, so this is joint work with a huge team of people. I've got 2 PhD students, Nicola and Miguel, who have both recently graduated, and they're off making piles of money in industry. So don't weep too much for them. Saf is a former PhD student. Actually, I should say Nicola and Miguel were both co-advised by myself and Alex Bouchard-Cote at UBC. Saf is Alex's former PhD student. And Ivy is a former master's student of mine, and I did my best to try to convince Ivy to stick around with me at UBC for a PhD. So it's a little bittersweet, but I'm very happy and proud that she ended up in your department. She's sitting right there. So a lot of the work today will be actually Ivy's work from her master's. Okay, without further ado, I'd like to start with a little motivating story of an applied collaboration. So this fellow here in the top left or top right corner, depending on how you're looking at it, is William Thompson. He's an astronomer. And William is particularly interested in exoplanetary systems. So in one project, he's been studying something called brown dwarfs. Now, I should say, before I get into this too much, I am not an astronomer, so I'm kind of unqualified to tell you any of like the technical details of some of like the data that we collected and some of the model parameters and things like that. But hopefully this is a good enough for like a statistics kind of audience understanding of what's going on here. Okay, so William is interested in these things called brown dwarfs, which are substellar objects. So they're part of stellar systems. They're bigger than a planet, so they're somewhere between 13 times and 80 times Jupiter's mass, but they're smaller than a star. So they're too small to fuse their own hydrogen. They don't generate their own light, except for a very small amount when they're first sort of formed. And what William and collaborators noticed is that many of these brown dwarfs are behaving kind of weirdly. So specifically, they are a lot more massive than we think they should be given how bright they are. So they do emit a little bit of light, and there's some good physics behind the relationship between how heavy they are and how much light they should be outputting. And the problem, especially with this particular candidate in the stellar system Gliese 229, this is Gliese 229b, which is this guy right here. You can see Gliese 229a is the star here. That substellar object is about 2 to 6 times less luminous than it should be, given its dynamical mass. Okay, so we know it's roughly its mass by how it orbits, and we can see its brightness by just, looking through a telescope at it. And it's not quite as bright as it should be. So what's going on here? William and collaborators discovered something incredibly cool. Specifically, Gliese 229b is not one brown dwarf. It's actually 2 brown dwarfs. They're orbiting each other as they orbit the host star. So they've got this kind of like spiral-looking orbit as they're sort of circling each other right around their shared center of mass. This is a really incredible discovery. The original discovery was published in Nature, and then there was a follow-up paper on the methodology, how they actually made this discovery in the Astronomical Journal. And you'll notice if you look closely, there's a bunch of the collaborators on that first slide that appear on that paper. So how did we actually get away with this? I mean, just, for scale, right? This star is a gajillion miles away. That's a technical term, gajillion. And the brown dwarfs are a gajillion times smaller than the star. And so the light from the star is totally washing out instruments. Like, this is incredible that we could even resolve this. The key technology that we used to do this was a Bayesian model. It's a Bayesian model. It's a very sophisticated Bayesian model. There's tons of parameters. I'll just go through a couple of them here. The main and sort of most important ones are these orbital parameters that tell you something about the geometry of the orbit. Okay, so like I'm on Earth and I'm looking way out at this system. If I were to describe the orbit of a sort of some kind of substellar object orbiting system, I would have to describe like the angle away from me and the angle that it's rotated in this way, and the sort of radius, the semi-major axes of the orbit, right? All sort of the Keplerian parameters. The 2 or n masses of the bodies associated with the system, the brightness ratios, and then some other technical parameters that are a little bit too in the astronomy weeds for me to go into. So the model is actually very carefully constructed, right? This is a sophisticated model. It's not just a black box. Like William and collaborators and us put a lot of effort into designing this thing really well. The data is super cool. The data for this problem is essentially 2 data sources from 2 different telescopes, the gravity and the cryo-res telescopes. The data tells you 2 things. So the Doppler spectroscopy, the idea of this is that if you look at a star and you see its color is oscillating, right? Star colors don't oscillate in reality. What's happening is the star is actually moving towards and away from you. It's oscillating in distance. And the reason why it's doing that, we think, is because there's a substellar object that's tugging it. So it's in an orbit that's sort of aligned with you, and that little planet or other substellar object is sort of grabbing the star and pulling it backwards and forwards. So the velocities we're talking about here are on the order of 1 to 10 meters per second. It just blew my mind to find out that we can resolve that kind of velocity on the distance scales that we're talking about here. So Doppler spectroscopy gives you something about radial velocity of the star, which then tells you something about the mass of other things in the system. In infrared interferometry, essentially there you're combining a bunch of telescopes. They act like one big telescope, and you're taking, at the end of the day, essentially a Fourier transformed version of a picture of the star system. And so with that, what you can see is sort of in-plane stuff, right? The Doppler gives you the radial component, and the infrared interferometry gives you the picture. Okay? So with these 2 things, you can put together your very carefully designed Bayesian model and data, and your posterior looks something like that. Woof. Right? If I'm sort of an applied scientist, I take a look at this and I run screaming. This is the pair plot, by the way. Each sort of row of this is a different variable in the model, as well as each column. And I'm plotting the bivariate marginals. Ignore the orange points. That's just some failed experiment that we were running. The blue points are really the posterior that we're interested in. So as a statistician, I look at this and I can see a couple of things that maybe worry me for traditional methods. For example, that's a 2D projection of some kind of helical manifold. The reason for this is, by the way, these angular parameters that live on a torus, right? We've got varying scale. We've got elements of the posterior that are much larger or much smaller than each other. We've got multiple modes. We have different competing scientific explanations for this data. And these multiple modes are meaningful, right? This isn't one of these like, mixture models, for example, where the modes are just because of permutation symmetries and I don't actually care about them. These are competing scientific explanations for what's going on in this system. And they're both sort of equally important. So suffice it to say that for a traditional MCMC method, this problem is super hard. But as I said, if I'm a scientist, I run away screaming from this. If I'm a computational statistician, I'm a kid in a candy store. So I boil this down to a sort of a crux of something, right? What are the, I guess, abstractified statistical problems, computational stat problems that we can pull out of this? And what I see are some common structures, like multimodality, right? And I think probably everyone knows exactly what picture I'm about to draw. If I have a multimodal target and I run a Markov chain to sample from it, I'm probably going to end up falling into one of two of the modes. And I won't notice that there's actually multiple modes. And as I said, in a scientific problem, this mode matters, right? I need to know about this potential explanation for my data. I also see varying scale, funnel shapes. And if I were to run a Markov chain on a posterior with a funnel shape, I'm likely to explore one part of the funnel well, but not the whole funnel. Essentially because Markov chains take a step of a rough particular size, typically approximately. And so depending on what size I pick, I might very, very well explore the sort of wide part of the funnel, but I won't even notice that there's a thin part. Similarly, we saw some kind of weird manifold structures. So I would call this a noisy manifold. It's not exactly attached precisely to a manifold, but it's in ambient space and there's some noise, but it's thinly concentrated around some kind of weird shape. When you run a Markov chain with targets that look like that, what you end up with is good mixing behavior across the manifold, the noisy manifold, and poor sort of diffusive behavior along the manifold, right? All of these, though, boil down to one sort of common problem, which is that MCMC is based on a Markov chain. So it explores well locally. And in some sense, it can only explore well locally because it's designed to maintain some kind of invariance, usually via reversibility, right? So the probability mass going from one state to another kind of has to match up with the mass going in the reverse direction. And because of that, you're constrained to make these local moves. What we want in problems like this is better global exploration. Something that you might think is, well, I'll look at my diagnostics and I'll see if things aren't working super well. The problem is that in practice, diagnostics like the effective sample size estimates that you might typically find, they're great at telling you whether samples look IID, but they aren't great at telling you whether samples have actually found all the mass that you could hope to find, right? Your ESS diagnostic for this sampler might actually look great because according to this sampler, I've got almost IID draws from a distribution that just ignores this. Right? So it doesn't even have to be these like multimodal cases. It can even be cases where there is sort of a connected part of mass. All right. So then the question is, if we've got these very nasty structures, how did we get those blue samples? That's kind of the point of this talk. I'm going to cover approximately 3-ish projects in this talk that all come together to create one sort of single automated Bayesian inference software. The first, and this is kind of the core component, is something called non-reversible parallel tempering. This is I guess what I would call an MCMC meta algorithm. It's a way of sort of combining a bunch of MCMC algorithms to do better than any single individual one. It was invented by a group in Japan. First author is Okabe, and this is back in 2001. It was kind of dropped since then. People haven't really used parallel tempering very much. And we will see why later in this talk. But the short and sweet of it is that it's really ridiculously hard to tune this thing well. If you tune it well, it works brilliantly. If you tune it even slightly poorly, it basically collapses and fails and does no better than just a single MCMC chain. It was revived recently by work by Saf Syed, who was one of those collaborators in 2022. He pushed the theory forward on it quite a bit, and in doing so came up with one of the tuning sub-algorithms that I'll talk about briefly today. We also have two other components, variational parallel tempering, which was out a few years ago, and AutoStep, which is Ivy's work from the last couple of years. These two are sort of other crucial tuning pieces for different parts of that non-reversal parallel tempering. These three come together into a software package, pigeons.jl. It's a Julia software for doing efficient distributed inference on compute clusters or on sort of like many-threaded machines. So I assume you guys at Dub have a good compute cluster here. This is designed specifically such that it satisfies a strong invariance property. If you run this software and take samples on any configuration, it will give you bit for bit the exact same answer, which is really good for debugging. Okay, there's a little QR code there if you're interested in checking that out. One little fun anecdote is that you might wonder about the name pigeons. So Alex, my colleague, is from Quebec, and he speaks Québécois French. In Québécois French, not Parisian French, in Québécois French, there's this verb piger. Piger means to pick something at random. And so pigeon, if you conjugate it, means let's pick something at random, or let's take samples. And so this is the genesis of that name. Okay. Before we get into the new stuff, let's talk about what parallel tempering is in case some of you have not seen it. So here's the gist. I have a target distribution, and I'll call that pi 1 throughout the talk. Think of pi 1 as like a very difficult distribution to take samples. And I have an easy distribution, pi 0. So think of that as like a Gaussian, right? We can sample from that super easily. I will call pi 0 our reference distribution and pi 1 our target distribution. The idea of parallel tempering is that it may be hard to sample from pi 1, but what I can do instead is construct a path of distributions from pi 0 to pi 1 by taking their two densities and raising them to a power 1 minus t and t. And then I let t go between 0 and 1. Okay, and what that does is it creates sort of an interpolating path of distributions from the easy one ranging to the hard one. And the hope is that by sampling the easy distributions and sort of exchanging information, I can help myself sample the difficult distributions. Okay, so we got to put this in a computer. So we're going to discretize the path to n plus 1 steps. So T0, T1 all the way up to Tn. We call those temperatures. Those are just different discretization points for that path. Then parallel tempering runs a Markov chain that is a much bigger Markov chain on a joint state space of an independent product of pi T0, pi T1, all the way up to pi Tn, which is pi 1. All right, let's do a little doodle of this. So if I had 3, n equals 3 as a little cartoon, usually n is a bit bigger than 3. I have my reference density here, the contours of that, pi 0. And then I have my interpolating path that sort of progressively gets weirder and weirder and weirder until I have my target density here with multiple bits. Okay. One thing that's worth mentioning is that you should think of all of these guys as sitting on top of each other. They're not side by side. I just can't draw them on top of each other on the slide. But in your head, think of them as sitting on top of each other. Okay. So if I'm going to run a Markov chain jointly on that whole space, I need to give them all a state. So I've got theta naught all the way up to theta n. And I'm going to iterate 2 steps to run parallel tempering, exploration and communication. The exploration step is quite straightforward. It's just run a standard MCMC step, any Markov kernel you want, on each distribution independently. So I'll run, let's say, HMC, right? And you can notice that this orange sample here, I do my little HMC trajectory, and it bounces off this choke point here. It's not able to explore. But you will notice that this blue sample manages to explore very nicely into this lobe over here. Okay, so exploration is just running a Markov kernel in each distribution. The next step, and this is where the secret sauce of PT happens, it's communication. I'm going to propose a swap between neighboring states. So imagine I propose a swap between theta 1 and theta 2. All I'm doing, remember, these are on top of each other. So all I'm doing is just relabeling. I'm calling theta 2 theta 1, and I'm calling theta 1 theta 2, just changing their temperature. I can formulate that as a Metropolis Hastings move, and I can accept or reject. And let's say I accept. If I accept, you'll notice now that I have taken a state from temperature 1 and moved it to temperature 2 in this difficult to explore region of mass. This is kind of the hope of parallel tempering, right? And then, of course, if I swap this guy over here, I'll end up in this second mode. And that's kind of the high-level goal of parallel tempering. The last thing I need to tell you is how do you do these swaps? As it turns out, and this is the non-reversible part of PT, you do the swaps by swapping all the even pairs and then all the odd pairs. So I would do 1, 2, and then I would do in the next round 0, 1, and 2, 3. So all the sort of independent, even, odd, even pairs. It turns out doing that gives you a very efficient algorithm, and doing the other thing you would think to do, which is randomly picking pairs to swap, is quite inefficient. All right. So that's it. That's kind of the secret sauce of how we solve that problem. But the question you should really be asking is, how did you tune this thing, right? Because now I don't just have one MCMC algorithm to tune. I have to pick a reference density. I have to pick n temperatures, and I have to pick n MCMC kernels. So you can see why people struggled to make this thing work over the last 2 decades or so, right? Especially these MCMC kernels. These are very, very difficult to design. Each one has to be adapted to each one of these targets. If anyone has used MCMC here, you'll know that even making MCMC work on one target is usually pretty challenging. There's no way I can ask somebody to do it for n, where n is usually like 20, let's say, something like that.
Wait, that's good.
Yeah, please.
What dimensions are we talking about for these problems?
So for the orbital problem is kind of, it's a nice little test bed to work in, because it's usually on the order of, well, depending on how you describe the orbital system, the problem I showed you is on the order of like 10 to 20 parameters. So it's not so bad. I've used this system for models with like 50,000 parameters. It scales the dimension. I don't have a slide on the dimension scaling of the theory that we've done. It doesn't, there's no cursive dimensionality. It's something like square root d, increase in cost for d dimensions. So yeah, it is sort of, it has a reasonable dimension scaling. Yeah, good question. Anything else before because after this, we're getting into the couple of like tuning technologies for each of these pieces. Okay, stop me anytime throughout if there are questions that come up. All right, let's start with the MCMC kernels, because I think that's the trickiest part. So I need to tune an MCMC kernel, tune the explorers. Most MCMC algorithms that I'm aware of have the following flavor. They start at a state x, and they propose a move to some x prime, and the step has a size that's approximately equal to epsilon, on the order of some epsilon, and that's a step size parameter that you have to take. If you pick epsilon too large, you reject your moves, you stay still. If you picked epsilon too small, you accept your move, but you don't move very much. So no matter what, you're getting these small moves. Parallel tempering makes this problem much worse, because I don't just have to pick one step size for one distribution, I have to pick n step sizes for n distributions, and they usually can't be the same, right? The reference is usually meant to be sort of big and diffuse to help with exploration, and the target is usually small and concentrated, and so you need epsilon to vary. Moreover, on problems where there's these funnel shapes, even one step size for one target is insufficient. You need to allow the chain to locally adapt, right? So also adaptive MCMC methods struggle here, because they ultimately find one good step size. I need small steps here and big steps here. So as the Markov chain goes between these two parts of the state space, I need the step sizes to change forever, basically. How do we do that? We're going to design a kernel that picks epsilon locally adaptively at each iteration. I'm going to base the exploration kernel on something called involutive MCMC, which is a very old idea that's recently made a resurgence in actually both in machine learning and computational stats. The idea of involutive MCMC is that I have a state variable x, I have an auxiliary variable z, and then I have an involution f with a step size epsilon. The involution is what's helping you make proposals. Okay, and the involution, the idea of an involution is that it's its own inverse. So if I apply f, and then I apply it one more time, I go back to where I started. How does involutive MCMC work? I pick a step size, I sample my auxiliary refreshment variable, that's like a momentum variable often. I make a proposal, x prime, z prime, using my involution, and then I accept or reject with some Metropolis Hastings probability. It's not super important. The important thing is that that step size epsilon is fixed. So I need to do something to pick it more intelligently. To pick it more intelligently, I'm going to add some auxiliary variables. Yeah, more auxiliary variables. A and B are uniform between 0 and 1. And we'll see their behavior in a second. They serve as sort of acceptance thresholds that I want to hit. I then compute my step size at iteration, whatever this iteration is, with my current state, my current auxiliary, and my two new auxiliary variables A and B, with the following mechanism. So on the y-axis here, I'm showing you the acceptance probability of a step of size epsilon, and on the x-axis, I'm showing you the step size. Right, as the step size gets small, probability goes to 1. As the step size gets large, probability goes to 0. I kind of want to be in that middle zone somewhere. So I use A and B, those auxiliaries that I just sampled, to define what I mean by middle zone, right? I want to have a step size such that my acceptance probability is somewhere in this, right? That's random, so I'm not making a hard decision about that. Then what I do is I start with a step size guess, epsilon naught. And if the acceptance probability is too high, I double my step size until it's not too high. So in this case, I would have to start by doubling, and then I would double again. And now that I'm below the threshold, I say that that's an acceptable step size epsilon. I can't just do this for free, right? If I do that, if I just pick that to be my step size and then do the rest of the algorithm, I've broken invariance. I don't have the right target distribution anymore. So to fix that, I need to fill in one more step here, which is that I need to compute the reverse step size from my proposal and make sure that they agree. Epsilon and epsilon prime have to be the same. If they're not, I reject, and I sample a new auxiliary and I go again. Okay, that is AutoStep. That is kind of the whole algorithm. It's a little bit to look at first, but ultimately it's really not too much more complicated than just the original involutive MCMC algorithm. So like random walk MH, MALA, HMC, these are all involutive methods. So as long as you can code those with a fixed step size, coding the AutoStep version of them is not that much more. All right, how does this work? Let's do a little toy example, a 2D Niels funnel, right? The hard thing about this is exploring on that x1 variable. The mean is 0, the true mean is 0. We're going to try to estimate that true mean. So here I'm plotting the estimate of that first margin mean on the y-axis here, and I'm plotting the scale of the funnel on the x-axis. So as you go to the right here, the funnel gets harder and harder and harder to sample from. This funnel sort of squeezes in. And you can see that nuts, which has a fixed step size, very quickly as I make that funnel hard, its mean estimate is biased to the right. So it's estimating its mean is like more around 12 or 15. Nuts is getting stuck over here in this right part of the distribution. Right? Whereas AutoStep for quite a long time is able to keep estimating that mean 0 quite well. It's exploring sort of the narrow and fat parts of the funnel by adapting its step size. Now, I should say, if you make this even harder, at some point it breaks down too, right? At some point, kind of no algorithm can cross that really, really nasty threshold. But it is certainly more robust for a wide regime. Yeah.
So I'm trying to understand some of the details of the comparison. So if you're using MATLAB, you're using longitudinal diffusion. So you're essentially using a Hamiltonian with Monte Carlo with one step.
Yep.
And so that will in itself adapt. I mean, it won't adapt. So your epsilon here is not really the step size. It's the, well, I mean, it is the step size, but
It's the step size for the MALA transition.
Which is now the variance of a Gaussian proposal in a random walk. So
no, not necessarily.
and in some sense, there is already some adaptation in MATLAB.
It is, but it's not quite good enough, I think, for this particular problem. You're right. MALA is kind of a bit of a non-trivial kernel because epsilon both influences the noise and the bias of the step size, or the bias of the step. But indeed, it seems like you need even more adaptation than what's from the fixed kernel, right? And I was that we tuned nuts here, so we did the best we could to get it to work.
The nuts is just that.
I think we did use scan for this one. Yeah, we might have used like the Turing implementation from Advanced HMC. I can't quite remember, one of the two, but either way, it's a standard implementation of it. Yeah. Yep. Good. Yes, please. So what I mean is x1, so this is a two-dimensional distribution. So x1 is the horizontal variable here. And I'm trying to estimate the mean of the x1 variable in this distribution. So the mean, we know mathematically is 0. This distribution is actually symmetric across this axis. Well, it's not symmetric, but the mass of the first, the marginal distribution of the first variable is symmetric. And so the mean is 0. So you can see that the mean estimate you're getting from nuts is sort of skewing off to the right. very quickly as the funnel gets more drastic. Yeah, the true mean is always 0 on this problem. Yeah. All right. So that's how this works on a cute little toy example. We also did some theory. In particular, we established that the chain is time invariant, irreducible, and aperiodic. Normally, that's kind of a rote exercise these days for most kernels. For this kernel, it's actually kind of non-trivial. And the reason is that at every iteration, you're making a very intelligent or like very careful decision on how far your Markov chain is going to move. And that can very easily break aperiodicity or irreducibility, right? Because there's not as much noise going on. You're like really choosing where you're going to make that step. So it's actually quite difficult to show that you haven't lost irreducibility and aperiodicity. But under mild conditions, it is. More importantly, I'm adding more work. I'm picking a step size every iteration, right? Turns out the number of iterations you need to terminate that step size is finite, almost surely. And we have bounds on the expected number of doubling or halving iterations. One example, we have more general bounds, but one example for a target that's whose log density is strongly concave and Lipschitz smooth, so like a Gaussian, more or less. We know that the number of doubling and halving iterations scales something like the absolute value of log of my original step size guess. So you can think of this as being the mistuning as this goes off to infinity. And so the cost sort of scales logarithmically in that, which is not bad. The ESS per step is mostly constant because we're adapting that step size. And so what you end up with is a cost or an ESS per unit cost of something like log epsilon naught inverse. If you compare that to a fixed step size method, the ESS per unit cost scales more like exponential of minus absolute value log epsilon naught, so exponentially worse. We verified that empirically. So if I plot the ESS per unit effort on the y-axis here, and on the x-axis, I'm showing you choices for epsilon naught, that step size parameter. In orange is the fixed step size method, in blue is the adaptive step size method. So you can see kind of what you would hope for here, right? If you tune the fixed step size method perfectly on these targets, and these are like normal, Laplace, Cauchy, they're very nice targets. They have one scale, right? If you tune that fixed step size method just right within a factor of 2, you outperform. The moment you're mistuned even just a little bit, you may as well be using AutoStep because it can account for your mistuning for you. Okay. All right, so that is AutoStep. And that's how we tune each of these MCMC kernels in each time. We just run AutoStep. And as we've just seen, the cost that you pay for the adaptation to figure out what the right scale is of each of these distributions is not so high, right? Yeah.
If you go to the previous slide,
Yeah.
just look at my lack of knowledge. So if somebody was just trying to do Mala and they had to pick epsilon 0, how did they go about that problem?
Usually you would target some kind of acceptance probability.
Okay.
So you look at, long run average of for you could do it a couple ways. For a given set of step sizes, candidates, you check their long run acceptance average, you pick the one that gives you sort of one that's not so close to 0 or 1. You can also do sort of like a stochastic gradient type thing where you modulate your step size every iteration and then it eventually settles down at a particular value. But either way, it's usually targeting an acceptance probability. Yeah. And so what this is doing is that, except it's doing it every single iteration, and there's no diminishing adaptation. It's always adapting, right? Yep, great question. Okay. So we now know how to tune the kernels, the MCMC and MCMC kernels. We just use AutoStep. So there's no human input on that, except that epsilon naught parameter. I'll get to that later. Now, this is the, let's say, slightly more heady, but ultimately simpler part of the technology, which is how do we tune reference distribution and the temperatures for parallelism. This is relating to communication, the communication part where you're swapping samples in between different distributions. So in order to tune communication, we have to talk about what it means to be communicating. What does good communication look like in parallel tempering? So here is a admittedly weird plot. Let's walk through this one. So on this vertical axis, what I'm doing is plotting different temperatures in my parallel tempering chain. So at the bottom here, I've got my reference. And as I move up the plot, I'm getting more and more close to my target distribution pi 1. I've got 30 chains in this plot, so n equals 31, I guess. Yeah, the maximum index is 30. And on the horizontal axis, I'm plotting iterations. So as the algorithm progresses, I'm showing you what happens. And the blue lines are showing you where the samples get swapped over time. So you can see there's like all crisscrossing as all the samples are moving around. This bold blue line, I'm watching just one sample. Okay, I'm watching just one sample as it gets swapped in between the different temperatures. And what I like to see is that. I like to see a sample that starts at my reference, where I get an IID draw. So I get fresh information. And it makes its way, maybe it rejects a couple of times, it comes up, it comes down, and eventually it hits that target. When that happens, I call that a restart. You can think of it intuitively as getting a fresh draw at your target, right? You're propagating new information to your target. So I want a lot of restarts. How do I characterize that restart? The rate of which I get restarts? So to do the math here, I need two assumptions, one of which is not so bad. In particular, I need to ask that I get independent draws from my reference. Not a big deal. You pick the reference. So pick a Gaussian, pick the prior, pick something that you can take samples from effectively. This is no big deal. This is the big assumption. I need something called efficient local exploration. At a very high level, what this means is I need my MCMC kernels that are operating to do the exploration. I need them to make the energy mix well. Okay. I don't need the state to mix well. So think back to that noisy manifold example. When I take one MCMC step, I move across that manifold really quickly. So that's mixing really well on the energy, but it's not mixing well on the state. But that's okay. As long as I mix well on the energy, my life is good. And the way that we've turned this assumption into math is we say that the energies actually immediately are independent after one step. This is not an assumption I would ever try to verify in real life. I don't think it ever actually holds in any real problem, but it's a really good model for how parallel tempering behaves when the explorers are tuned well, which is kind of what we're hoping for. If you're willing to play along with me and go with these assumptions, mathematically, this decouples the complicated exploration MCMC kernel shenanigans and lets me just look at this index process for the communication. And in particular, this lets me write the following statement. The restart rate, the rate at which I get those restarts, is given by 1/2 + 2 lambda n, where lambda n is called the n-chain global communication barrier. And it's just the sum from all the chain pairs of the rejection rate for pair n. So I just look at how often am I proposing swaps and getting rejected. I sum those all up and then obviously 1 minus Rn. Okay, so this sort of integrates over the chain, over all the chains, how likely am I to really successfully propagate a sample all the way to the end. One thing that's worth asking if you're sort of an MCMC theoretician is, okay, Trevor's talking about restarts and communication and how they sort of correspond to each other, but do I really care about this if what I care about is the convergence of my MCMC chain? And the answer is yes. If I look at this asymptotic limit where I have as many chains as I want, so I'm on a big compute cluster and I have 10,000 different chains operating together, we can show that the restart rate converges to this thing called the global communication barrier. So it converges to a constant as n goes to infinity. And that constant has a deep relationship to geometric ergodicity of your parallel tempering chain. In particular, if I scale time by n, right, because I'm increasing the number of chains, so I'm discretizing that path more and more and more. So I need to scale time by n. But if I scale time by n, the total variation between my target chain and my target, or my last chain and my target, decreases geometrically with a constant proportional to 1/lambda. So I want that communication barrier to be small, right? I want to minimize that global communication barrier. And by doing so, I maximize the sort of convergence, or minimize the total variation error between my my Markov chain and my target. Fun fact, that constant is 1.2, universal. Unfun fact, I could not show that. The best that we could do, and this took months and about 60 pages of complex analysis, which I never thought I would use in this job, we got it down to 106. That's the best that I could do. If you can beat that, please tell me. And as I said, the problem that this boils down to is bounding some really nasty complex integral. And it turns out it's about bounding the poles of that integral. And so you can see we've got a cute little complex math diagram here. And you can see all these little poles going off, right? You need to bound the location of that pole. And you need to show that there's no other pole that's to the right of that pole. Turns out to be a very hard problem. Actually, at some point in this, we were worried that this was equivalent to the Riemann hypothesis. And so we were like, should we even bother proceeding here? But we persevered and we ended up getting an answer. It is not equivalent to the Riemann hypothesis, thankfully. All right. So, okay, so using that information, we know that the n-chain global communication barrier characterizes our restart rate. We know that it characterizes ergodicity of the chain, so we want to minimize that thing. How do we minimize that thing? The idea is that if you look at that formula, that term is going to be dominated by this 1 minus Rn. If there's one Rn that's close to 1, we're toast. Intuitively, what that means is that if I have my path of distributions going from my reference to my target, if I have a gap, if one of those rejection rates is high, if I have a gap here, I'm sunk. I can't propagate samples along that gap. And so parallel tempering just stops functioning. This is why it's really hard to tune PT, because this problem killed people for years. This comes from the fact that people traditionally have used evenly spaced temperatures. So Tn is sort of, 1 over n, basically, or k over n, I suppose. The way to fix this is to use unevenly spaced temperatures, right? Find a way to fix some unevenly spaced temperatures so that I can evenly space my distributions along the path. Balance out the rejections. You'll see that your rejection rates, Rn, generally are going to be a little higher everywhere, but there's no big gap anywhere. So you don't have this choke point in your swapping scheme. Okay, so SAF showed that making sure that the Rn's are even minimizes lambda n. And furthermore, derived a methodology for automatically tuning these temperatures in an uneven way to get evenly spaced rejection rates. I have a slide after the end of the talk if you want me to show you how that actually works. Suffice it to say, there's no gradient tuning here. You basically just estimate the rejection rates and then reconfigure the temperatures to try to predict where the temperature should be to make the rejections even.
Do that as the algorithm.
I'll show you when we do that as it progresses, because indeed, if you were to do it every iteration, this would be kind of unstable. I wouldn't recommend doing that. We'll get there. We'll get there. So the last thing we've got, yes, please.
Is it true that for the intermediate distribution, the support is the union of the first and the last supports?
Is it the union or is it the? It might be the intersection. I think it might be, because if you take the product of two densities that are disjoint, it's just 0 everywhere, right?
Right.
So I think you have to make sure that they share support, typically, the reference and the target. But that's usually not such a big deal because a lot of the time people use software these days to automatically transform parameter spaces to just be the ambient RD. And then you can just do all this on that ambient
That
space.
was that very weird shape for distribution.
So the weird shape's not a problem as long as the support of the distribution is the whole ambient space. The problem is if you're actually on a manifold, right? You're actually constrained to like a spherical manifold or something like that. Then you have to do something special. You have to do some kind of manifold constrained Markov chain. But for the problems that we have, generally speaking, the data forces you to be near a manifold, but not on the manifold. So you have, even though the probability can be vanishingly small outside of the manifold, it's still there, right? So that orbital example I showed you, yes, if you look at the samples, there's no samples on large parts of the state space, but the probability density there is positive, technically. It's just very small. Yeah, very good question. All right. So we've got the temperatures, we've got the Markov kernels. Let's do the last thing, which is the reference. So once again, the idea here is that if my reference and my target are very different, there's not much overlap between these distributions on the path. So the swaps get rejected. So we have a low restart rate. So we have a high global communication barrier. We have slow MCMC convergence. Naturally, what we would rather do is have something where the reference is much closer to the target. They should be similar. They have high overlap. Your swaps get accepted. You have a high restart rate. You have a low communication barrier. Good MCMC convergence. Traditionally, people set this to the prior. And this does not work. We can actually show provably that it works very, very poorly. Our idea here is instead to not just fix it to the prior, but to actually choose some kind of variational family and optimize the parameters of that family to sort of roughly match the target distribution with our reference. Anytime someone brings up variational inference, the first question should be, what family are you working with? For a long time, in fact, I have an entirely separate thread of research that looks at designing really, really good variational families that are they have theoretical convergence guarantees and blah, 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 blah. For this problem, here's what we want. Something that works. It doesn't fail. It doesn't like miserably blow up in some cases. And it gives you let's call it a quick and dirty, decent fit. Something that just roughly covers your distribution, right? What I want something something that looks like this. I want this orange. I want to just like roughly cover the distribution. I want to roughly cover it. I want to roughly cover it. I don't care if I'm getting a good approximation because parallel tempering will handle the good approximation part. I just want something that will help me move samples around the state space. Okay. So there's a lot of theory behind this, and I'll just introduce one result, which I think is quite illuminating. And this is why, again, PT has really struggled to work in the past because people have used the prior distribution as their reference. If you have a Bernstein von Mises-like posterior, so a posterior that kind of concentrates around a Gaussian, or it becomes kind of Gaussian-like, it concentrates, then in the data asymptotic limit, if you use the prior, your global communication barrier screens off to infinity. Right? Your algorithm becomes more and more and more inefficient. Meanwhile, if I were to say pick a Gaussian and fit it using moment matching, so no iteration, no gradient descent here, just match the mean and the variance, we can show that the global communication barrier between that fit family converges to 0. Now I'm sweeping a lot of the rug here, right? You'll notice I'm not making any probabilistic statements here. I'm not saying almost surely in probability, whatever. There's a lot of math that goes into that, and I would encourage you to check out the variational PT paper where we do that properly and rigorously. But this is kind of the intuitive picture of why you really want to tune your reference.
For example,
Yeah, please.
that's what I had in mind. So in that example, you have like this narrow shape distribution, and then you have the Gaussian as a reference.
That's right.
So how would you accept like the first?
Yeah. So the trick is that you have a path of distribution, right? So I start with this orange. That's temperature 0. Temperature 1, it's kind of Gaussian. It's still, but it squeezes just a little bit towards the manifold.
But if it's an intersection of supports, how can it ever be?
The support of this guy has to be full support. So even though I'm drawing these contours near this manifold, this probability distribution has full support on the full state space. It's just that the probability of being here is vanishingly small. Right? But it's not 0. It can't be 0. If it's 0, this will not work. Right? Well, okay. It won't work well. Yeah, because I made a very incorrect statement here. Most of the probability mass in high dimensions is not going to be anywhere near this, right? So you're going to run into problems. If you are constrained, you have to reject a lot of samples if you have hard constraints. If you have soft constraints, the interpolation saves you, right? So just don't use hard constraints is the point that I'm making, right? Allow yourself to be off the manifold, even if the probability is vanishingly small. Yeah. Okay. So this comes back to Abel's question, how do we actually do the tuning, right? I've given you some little bits and bobs and they each have their tuning parameters. How do we tune those things? The idea is that we're going to run parallel tempering as an inner loop with a very slow, increasingly slow outer loop. I'm going to initialize my variational parameter to whatever identity, right? Just Gaussian 0, 1, no big deal. Start with evenly spaced temperatures and set my initial step size gets to 1, right? Always do this. It really doesn't matter. In tuning rounds, I'm going to take 2 to the R draws, so exponentially increasingly many draws from parallel tempering using my current tuning setup. Then, given those draws, I'm going to tune in closed form, no iteration, no parameters, the temperatures to set equity rejection, the variational inference, the variational reference via moment matching, and the auto step initial step sizes. There's many ways to do this. We've usually done it by looking at the median of the step sizes that were actually chosen in every iteration. And then you just run this loop, right? This stabilizes generally quite quickly. I would say 6 rounds in my experience is usually enough for this all to stabilize reasonably. Some problems are harder. Okay. Critically, there's no user input here. This thing runs totally autonomous. As a little fun experiment, let's examine the effect of that reference and temperature tuning. We've sort of seen the effect of the step size tuning already. Here's a different problem from composites manufacturing. The gist of this is that I'm cooking like an aircraft wing or a bike frame, a carbon fiber frame, in an autoclave, and I get sort of point temperature measurements of it as it's cooking, and I want to infer the structural state of the part. So it's quite a complicated setup. I won't go into the details. The point is that we ran this algorithm on this complicated problem, and I plot the number of restarts that my parallel tempering scheme gives me as a function of the number of iterations. So obviously higher is better, right? Purple is the baseline where I don't tune either the reference or the temperatures. Green is where I only tune the temperatures. Red is where I tune only the variational reference, and blue is where I tune them both. Again, this is the perfect illustration of why PT has not really been used too much in the last 2 decades. Because unless you tune it really, really well, you get nothing. And it's basically, you're doing n times as much work for exactly the same result as you would have gotten originally. If you do tune well, you do get a sort of ramp up of increasing fresh information at your target every so often, which is usually quite good for global exploration. And as I said, yeah, that's around 6 there, where it stabilized, and you can see that the restarts start to take off once you've tuned reasonably well. One little last example, if I use different variational reference families. So for example, I could use just a Gaussian with a diagonal covariance, could use a Gaussian with a full rank covariance or a dense covariance, and I could use the prior. We've done experiments on all kinds of models, GLMs, unidentifiable regression models, ODE parameterization, predator estimation, mixture models, the list goes on. I'll just show you 2 here. This is a pretty typical comparison. Number of restarts on the y-axis, number of iterations on the x-axis for both of these. Blue is the prior. This is what people would have used in the past. This is with temperature tuning, by the way. So I've enabled temperature tuning for all of these. With a diagonal Gaussian, we actually get quite a bit of benefit. So that's an order D tuning exercise. That's actually quite cheap and very simple. If I go all the way to a dense covariance matrix, I get a little bit more benefit. However, this plot is cheating a bit because we're not plotting computation cost. I'm plotting parallel tempering iterations. There's a D squared cost for fitting that. And you also have to invert that covariance matrix. So that's D cubed, right? So this is hiding something. Usually if you actually plot restarts versus cost, this line comes down below the diagonal Gaussian. So our recommendation and what we do in our Pigeons package is just to keep that at the diagonal Gaussian typically. Okay, that is it for me. I have found through my work, so I use this in consulting now as well, all of my consulting projects. It's one of the things that works broadly, parallel tempering, but only if you can tune it well. So we have now fully automated methods for temperature tuning by essentially minimizing the worst case swap rejection rates or making them even. Reference tuning by round-based variational inference, and explorer tuning via automated locally adaptive methods. And then we have that very long, very scary paper on convergence theory. The results are very clean. The proofs are very not clean. And as I said, if you're interested, here's a broken QR code with a little arrow in the middle, so you can't use it, unfortunately. But ask me if you're interested and the URL is quite simple. It's pigeons.run, because .fly wasn't an acceptable suffix. Anyway, thank you.
There is quick questions. Yeah.
Go back to the other step slide.
Yes, I can. It will be, so close your eyes for a second because it's going to be a little messy.
Yeah. So could you explain again why you need the A and B?
This is a really good question. So what I don't want to do is to have to pick a hard decision on what is an acceptable probability. What I want to do is say, close to 0, no good. Close to 1, no good. But aside from that, hands on. You could indeed use a different distribution for this, but I would encourage you to use a diffuse distribution no matter what, right? Because you don't want to make any kind of hard decisions on what acceptable means, right? So all this is doing is intuitively keeping you away from down here and keeping you away. Yeah. With the understanding that MALA, the optimal in a high dimensional scaling regime is like, what is it, 0.634 or 574 or something like that. I can't remember quite what it is, but it's in the middle here somewhere.